And we have this while my slide gets up. Okay, what I'd like to talk about is an experiment that we're working on. It's a portion of the Lunar team, which is a portion of the Lunar Science Institute. This consists of laser ranging to retroreflectors on the moon. Back in Apollo days, we left some retroreflectors on the surface of the moon. We've been ranging to those for 40 years. Next slide. And as far as the moon is concerned, there have been a large number of results from this. Most obviously, the discovery of a liquid core, published about 5 years ago, and a very precise selenoidetic network. In other words, we can get these positions to a meter or so. And in general, by studying the long-term motions, in other words, making the distance measurement repeatedly. One example, the sloshing of the liquid core is what we see in the lunar librations. Next slide. And also in general relativity, a good proportion, maybe most, of the best tests of general relativity to date have been done with the retroreflectors. I'm going to talk a little bit about some of the issues on actually creating such a package. Fabrication, we've already demonstrated that this can be done to a factor of 3 better than standard procedures. And we get a sufficient return. What I'd like to talk about is the optical and thermal issues having to do with performance. When we go to from a small retro to this larger one, 100 millimeter, thermal behavior becomes a very critical issue. Next view graph. How do we go about this? Well, first we have to make and this is a life-size model, we have to make a computer model of this, both in AutoCAD and in IDL. Next slide. And so all these components are retro, the sunshade, housing, and thermal shields. And this basically is the these are the elements of the package, and it's creating a simulation of these in order to go with the next analysis. Next view graph. The Thermal Desktop is a commercial program that takes, first is the IDL, a program generated at the University of Maryland, in which we take at present 1,000 rays. Each one of them goes into the corner reflector. At each millimeter, we take the absorbed, and we cut up the solar radiation into 1 nanometer bands. Each one of those goes into the absorption at that millimeter. Part of it's absorbed, part of it's continued. And so we do that for 1,000 rays, and then repeat that for several hundred orientations of the sun during illumination. This amount of heat that's deposited is then passed on to a commercial program thermal desktop developed by CNR Technologies. And for that, it converts these heat deposits into temperatures. And so now we end up with a, next slide. Oh, I've already said this. So this is going back to the deposition of the energy. So we have a four-dimensional map of where this is deposited. Next view graph. So thermal desktop then converts this heat deposition or power deposition into temperatures. And so here we have the simulation of how the retroreflector behaves. Results, the absorption in the corner reflector, now ignoring all this nice housing, results in a delta T of the order of 0.2 of a degree from the tip to the surface, which is what's the important part. Next view graph. Once we have the temperature in 3D, we have to convert that to how does the light come in and how does it come out. The light going in is plane wave. And so what we have is a rays going through this, looking at what the temperature is, converting that into index of refraction, and then tracking how much the phase of that light is delayed by going through these temperature inhomogeneities. Next slide. Oh, I'm not going to go through all this. But this model, I did not bring the retro with me this time. I'm sorry, this will just go in and stay. The advantage of, as you mentioned, of these retroreflectors, for those not in the game, is that when the light comes in, it goes out in the same direction. That means that if I'm sitting on Earth and I'm shining a laser at this, even though things are tipping, on the moon, the light comes right back to the observatory. And so that's the only way, even with that efficiency, we send out 10 to the 23rd photons, and we're happy when we get one back. Velocity aberration, I'll worry about later. Yeah, and so therefore what we do is we take the corner reflector and we tip one of the back faces a little bit, and that puts the light back to the observatory. Next few, and then, sorry, go back. Then what we also do is we've converted it into a phase. Then we convert that by taking fast Fourier transforms into the behavior back on Earth. In other words, the far field diffraction pattern. So from that, we can get what the return will be. The offset, which we talked about, is taken care of by code 5. And that then we say, well, we've got all this too much data. And how do we handle that? Because we have to make tens or hundreds of runs. Next view graph. So here we get the deposition of energy at solar noon as a function of depth in the corner reflector. And then we also look at things, what happens during an entire lunation. And then the more interesting thing, next slide, is what is the return signal? These are the return signals for Apollo 15 and Apollo 11. Apollo 15 is a retro currently on the surface of the moon, which a number of stations can get to. And so what we would like to do is to get the same kind of return for our package here. And this is, but this indicates problems on the present retroreflectors. There's a large dip at lunar noon. On the other hand, again, for just the corner reflector, we're still optimizing surfaces in here. We get essentially a constant return through the full lunation. And essentially at the Apollo 15 return. This is what we would receive at Maui, one of the lunar stations. Next view graph. Next question is, how do we get there? We could wait for, I think Jim said that the ILN is going to be something beyond 2020. I was on the original Apollo team. I'm not sure I'm going to be around 2025 in order to participate. So the Google X Prize people are planning to be up there in the next 2 years. This is the model for Moon Express. This is the corner reflector mounted on it. Both of them are full-size models. And these are some of the participants. This is Bob Richards, who's head of the group over there, and Alan Stern, as well as some of our people. Next view graph. So there are two issues on this. One is we get a ride there. And what I would like to do is to say to them, well, you got to line your spacecraft up like this and put it down where it's level. And then I can point right back to the Earth, because this does limit my field of view. On the other hand, they're not promising that. So what you've seen here is what we're going to use in order to do the pointing. We'll mount this and have stepper motor drives. And then, next view graph. Small camera up here, and we'll center the Earth in the view of that. Hopefully, let me add one thing which I should have done at the beginning. Why are we doing it again? We've got packages up there. The difficulty is, or the advantage is, that ground stations have improved a factor of 200 over the past 40 years. What we put up was an array of 100 or 300 for Apollo 15 corner reflectors. The moon goes like this. We don't know whether the photon came from the faraway corner or the near